All right, for this circle exploration, it's best if you have a printed copy of this handout. If you don't, you could certainly use a notebook piece of paper, or you could preferably have a piece of graph paper to help out. So what I want you to do as we're working our way through this is I want you to try it and then pause the video, try it, and then come back to it, because I think if you actively try to do these tasks before I do, you'll learn more than if you just follow along and do what I'm doing. So I want you to start by sketching a circle with a radius of 2. So here's where you'd pause the video, sketch a circle with radius of 2, and then start it back up again. In my experience, this is what most students do. They create a circle with a radius of 2 centered at the origin. Well, radius of 2 means from the center to any part in the circle is going to have a distance of 2. So on number 2, we're asking, what is the radius of this circle? That's right, 4 to the right, 4 to the top, 4 to the left, and 4 to the bottom. The circle has a radius of 4. And on number 3, I want you to find the length of the radius of this circle. That's right, from the center to the circle is a distance of 3. On number 4, we want to figure out what's going on with this particular circle. So notice that it has a total of 4 triangles in the circle itself. And we want to write an equation that will help us find find the length of r, the radius. And we'll start with this triangle that has a point of -3, 4. That's part of the triangle. So we have a triangle, a vertical piece, a horizontal piece, and then this piece that represents the radius of the circle. So hopefully you recognize that when we're looking at a triangle and it has a vertical and a horizontal piece, that those are perpendicular to each other, and so we have a right triangle here. And hopefully you recognize that with any right triangle, our leg squared plus our leg squared is equal to our hypotenuse squared. Pythagorean theorem, a squared plus b squared equals c squared. But in this case, because what we're looking for, the hypotenuse, is the radius of the circle, we'll substitute the letter r in. So let's check and see, how does this particular guy work? Well, we went 3 to the left from the origin, we went 4 up, and so -3 squared plus 4 squared equals r squared. 9 and 16 is r squared, so r squared has to be 25. That means if we take the square root of both sides, r will be a positive or a -5, but in geometry's case, we typically don't talk about segment lengths or hypotenuses having a negative value, so we call it a plain old 5. So I want you to try this out and decide, does this equation that we used above work for the triangle with the point -3, -4? Will it work for this blue triangle? Why or why not? Will it work for this orange triangle that has the point 4, 3? And finally, will it work for this green triangle that has the point 4, -3? So number 8 asks, what is the length of the radius for the circle above? We found out that that was 5. And number 9 says we want to find an equation for any point xy that would satisfy the graph above. So it doesn't matter if it's the 0.43 or the 0.34 or the 0.05 or the point -50 or even any of these little numbers, these little points along the circle that don't go through the grid work nicely. We want to know what would be an equation that would work for any point x, y. So even this tiny little equation, or tiny little triangle, or this triangle with this tiny little angle, what would be the equation that would work for that point x comma y? Well, it's still a right triangle. It still has two legs, so one leg squared plus the vertical movement squared has to equal the radius squared. And so we've just discovered the standard form of an equation of a circle centered at the origin with a radius that has a length of r, as x squared plus y squared equals r squared. All right, so if you have printed on the back, let's flip to the back side or second page of the paper. And now we're going to work with some other, actually we're going to finish this piece up, my fault, at the very bottom of the page and see if we can figure out the equation of these circles. So any circle centered at the origin is going to have an equation of x squared plus y squared equals our radius squared. What's the radius of this particular circle? That's right. And 6 squared is 36. I'll leave you to do numbers 11 and 12. So now we're on to the back side of this paper, and I want you to sketch a circle centered at 1, 2 with a radius of 2. So again, pause the video anytime you need to do the work first, and then start it back up again to see if your work matches mine. All right, so hopefully you have a circle centered at the point 1, 2 with a radius of 2. Now we want to find the center and the radius of this particular circle. So looks like we have it crossing here, and we're going to go 1, 2, 3, 4, 5, 6 across. Half of that is 3, the midpoint. So 3 up, 3 down, 3 left, 3 right. So it looks like our radius is 3. And that point, that is the center, is 5 to the right and -1, and 1 down. So -1, 5, -1. Then let's sketch a circle with a center of -3, 4, and a radius of 5. Once you're finished with that, I want you to compare the solid and dashed circles here. We want to know how are they similar, and then how are they different. So how are they similar? Hopefully you notice that they are the same size, or that they have the same radius. How are they different? Other than one's dashed and one's solid, hopefully you notice that they have the same, or they have different centers. So what point is the center of this dashed circle? Well, it looks like we went 8 across, so 4 in, 4 up, 4 down. That looks like our center. So that center is the 0.32. And we want to know how is the center of the dashed circle related to its equation. Well, the center of the dashed circle was 3, 2. Let's write that up here. And the equation of the dashed circle is x minus 3 quantity squared plus the quantity y minus 2 squared is equal to 16. Well, that makes sense. We went 4 to the right, 4 to the left. So this is our r squared, 4 squared, 16. And notice that the 3 appears in this equation, but it's the opposite sign. And the 2 appears in the equation, but it's the opposite sign. In fact, this is the x-coordinate, this is the y-coordinate, so it looks like the x is with the x, the y is with the y, but the the signs are the opposite. And so how is the center of the dashed circle related to the equation? It appears in the equation but with an opposite sign, or with opposite signs. So we want to know what is the center of this circle. Well, if we're right, it looks like we should be switching the sign of the x-coordinate. Instead of a +2, it should be a -2. Switching the side of the y-coordinate, instead of a -3, it should be a +3. And this radius should be, well, 5 squared is 25, so it looks like it should be 5. So let's check. If we go 2 to the left and 3 up, did we get the center of our circle? Well, 5 to the right, 5 to the left, 5 up, 5 down. Yep, that is our center. So now we want to graph a circle with a center at 1, -3. And then we want it to have a radius of 3. And then we want to write the equation of this circle. So x, opposite sign of the 1, squared, just like a squared, plus y, opposite sign of the -3, squared, equals 3 squared, or c squared, r squared. And I finally want you to, for the last one, I want you to write the equation of the circle in number 22. So it looks kind of scary, right? But it's actually just Pythagorean theorem in disguise. If we want the standard form of an equation, no longer centered at the origin, but it's centered at the point hk, h for the horizontal movement, the y or the x movement, k for the y movement, the vertical movement, with a radius of r, all we do is we say x, change the sign of the x coordinate of the center and square it, plus y, change the sign of the y coordinate and square it, is equal to r squared. Thanks for watching.